Okay, so in this revision video, we're going to be going over oscillations, and I've structured it like this. We're going to be going over oscillations. First, we're going to be going over the velocity, displacement, acceleration, and some basic things. And then we're going to be going over equation of time, period, and frequency. And then last but not the least, we're going to be going over a big part of this chapter that usually is a bit more tricky, and that is resonance and damping. So first, let's understand some basic terms. So first of all, you have to understand, what does amplitude mean? Okay, so amplitude would mean the maximum displacement. And remember that displacement can be negative and positive. So we can have both negative displacement and positive displacement. It is a vector quantity at the end of the day. Right? Okay. Next thing, time period. So time period is time taken for an oscillation, for one oscillation. Okay. And the symbol for this is going to be capital T. Remember, whenever you write capital T, that shows you the time period. If you're going to draw if you're going to write a small t, that's going to be showing you any time. Okay. And then we have angular frequency, which is going to be omega. And angular frequency is basically the rate of change of angular displacement. So the rate of change of angular displacement, omega, which is the angular frequency, is equals to theta divided by t, or 2 pi divided by capital T. Notice the capital T is for a full oscillation, and the full oscillation is always going to be 2 pi. Okay. And then you can see that here theta and 2 pi, it just shows you that our angles that we're going to be taking are going to be in radians. Next is a word that you might have seen in your wave chapter. That is phase difference. Okay, phase difference is the difference of phase angles of two oscillating quantities at a given time. So for example, I'm going to draw this wave, and then I'm going to be drawing this oscillating wave. The phase difference between both of them is going to be 180 degrees, or pi by 2 radians. Okay, or pi radians actually. About pi radians. Right? Notice that they both move in opposite directions. So this is going to be moving in negative direction. The other one moves in the positive directions. Basically, they're moving opposite to one another always. And if they move opposite to one another, we say they're antiphase. Antiphase simply means that their phase difference is pi radians or 180 degrees, right? And then you can have many other examples of this as well. So it's good to understand this as well, because a lot of old spec papers have these type of questions where they ask you about the phase difference of two waves, or two sine curves or cos curves. If you're a math student, you would get it, right? This is going to be sine x, and this is going to be minus sine x. Okay. Now, next thing is that what is an oscillation? It is a periodic and repeated motion. So you can have circular motion, heartbeat, springs. So all of these are examples of oscillation. And the main type of oscillation systems that we're going to be looking at is mass spring system, which is going to look like this, and then pendulum, like this. Okay, I'm sure you're familiar with all of this. So that's the basic terms. Now let's move on to the definition of simple harmonic motion. So I want you to pause the video and read through this, which I hope you already know. Okay, so remember, there are two conditions for simple harmonic motion. The first one is that the displacement from equilibrium position should be proportional to the resultant force. Now I'm writing it like this so it's a bit quicker, but you have to write the full thing in exam. And then remember, the resultant force is in the direction of equilibrium position. Okay, And third thing I will list as well is that the resultant force is in opposite direction to the displacement from the equilibrium position. So remember to always specify that the displacement is from the equilibrium position. And the equation for this is going to be from Hooke's law. F is equals to minus k change in x, where the minus sign is going to tell you the direction, that both of them are in opposite directions, and this is that resultant force, or the better word for this is restoring force, but the mark scheme include, they say resultant force, but I definitely prefer, if it were me, if I were the examiner, I would say restoring force, because it makes a lot of sense. Okay. As for what restoring force is, or what this resultant force means, I recommend you check out the video that I've made from the oscillation playlist. Okay, so that's this. If you want, you can pause and read through this. You can also plot a y is equals to mx graph for this. And yeah, that's all. Okay, next we're going to be looking at another equation. We're going to be looking at acceleration is equals to minus omega square x. So this is another very interesting equation. And you can plot a graph for this, y is equals to mx again. And this has come up in exam, this exact graph. Okay, and the graph would look something like this. And notice that this point here is the maximum displacement. So this is the amplitude. Okay. And then using all of this, what you can find is you can find the gradient. And the gradient m is going to be equals to omega square. Okay, you can ignore the minus sign. And then you can square root the gradient and you can get omega. And when you get omega, you can find the time period. So that's going to be really helpful. So the next thing we're going to be looking at is plotting the graph of displacement against time, velocity against time, and acceleration against time. So in Edexcel, we always make the assumption that we're starting the time from the equilibrium position. So that's just a thing that we should always just keep in mind. Okay. So we're going to start from the maximum point or the amplitude. And you can either use a computer to plot this graph, or you can use your sand and paper also. There's a technique of that as well. So either way, you're going to be plotting a graph of displacement against time. And the graph we're going to get is x is equals to a cos omega t. Okay, this graph is there, this equation is there in your data booklet as well. Okay, and this here is one full cycle, and this is going to be the time period. There's a positive sign here. Now, this positive sign and this cos, they're going to tell you the shape of the graph. So if they ever ask you, they have asked a graph, I think it was velocity against time graph, and they asked you to plot it with a bunch of equations and values given, and it was around 6 marks. Okay, and then this here tells you this A here tells you the maximum point and the minimum point of the graph. So this is the max and minimum point of the graph. So this here is going to be A minus A, and this here is going to be plus A. Okay, and then this here is going to be omega, and then the time t. Okay, so that's the first graph. The second one is, if you know differentiation, it should be really easy. If you differentiate dx by dt, you should get velocity. Okay, so we get velocity. If we differentiate this, we get velocity. And then, if you differentiate this entire expression, you get a omega minus sine omega t. We're differentiating with respect to t, so t is not going to have anything that's going to come here. It's just going to be omega, that's going to come here. And then cos is going to become into minus sine omega t. Okay, so we get this as our expression, and the graph for this is going to be v t and then minus sine. Okay, and then here our maximum points are going to be a omega, right? A omega is the max. You can write here max or minimum displacement, and here max velocity. So we can say x maximum value of x is a, and maximum value of v is a omega. That's another very, very, very important equation. And then you further differentiate this again, you're going to get acceleration is equals to, differentiation of minus sign is going to be minus cos, so minus a cos omega t. Differentiate the omega t, you're going to get omega again as well, so it's going to become omega times omega, because we had the omega before as well, so it's going to become omega squared. Okay, and then for this again, the graph is going to be it's going to be a minus cos graph, so it's going to be something like this, something like this. Okay, a t. Okay, and then the maximum value of a is going to be minus a omega squared. So the maximum value of a max, is a omega squared. Okay, so this is going to be the maximum value, and this is going to be the graph for all of them. Now, if you do not know differentiation, that's totally fine. I'm going to tell you a rule, you memorize it, this is going to become very easy. There's many other ways to do this, right? If you notice, then your x and your a are always in antiphase, right? So you can think of that as well. And the movement of them, you can think about it as well, that all of them shift by t/4 as well. But I'm just going to tell you an easy technique. You memorize. It's really, really quick. There are many ways to do this, but I prefer the one I'm going to show you. Okay. Anyways, so basically how this works, x, you have this equation, v, you have this, a, you have this. Just memorize this. If you're not a math student, totally fine. As long as you memorize it, you're good to go. Okay. Now, coming to the graph part, right? I want you to memorize this rule. Okay. If I'm going to differentiate sine x, I'm going to get cos x. If I'm going to differentiate cos x, I'm going to get minus sine x. Okay? And integration works like this. So if I have my sine x and I integrate sine x, I'm going to get minus cos x. And if I get cos x and I integrate cos x, I'm going to get sine x. Okay? So if you memorize this, your graph should be pretty easy. But if this is a bit difficult, then you can memorize this rule as well. Okay. 1 second. For velocity, if you want to change the x graph into the velocity time graph, you look at the gradient. If you want to change the x to time graph into acceleration to time graph, you basically invert them, or you just make it antiphase. Okay, they have to be antiphase to each other. Okay, it's like multiplying the entire graph by a negative value. So for example, this is your x against t graph. So how would you plot the v against t graph? You look at the gradient. Initially, gradient is max, gradient is maximum, gradient becomes 0, gradient is maximum, gradient becomes 0, gradient is maximum again. So it's going to become something like this. So you look at the gradient. Okay, and then for the a against t graph, you just make it antiphase. So you just multiply everything by negative value and you just flip the graph. Okay. And if you find integration differentiation easy, I know many of math students are there, they find this really easy with integration differentiation. So with that technique, if you want to go, you just differentiate as you move forward. And if you want to move backward, you integrate. Okay, and that's how I typically teach my students as well. Alright, so that's all for this part. Okay, so now we're going to talking about energy and maximum velocity. So maximum velocity we've already seen is a omega, and then our EK we know kinetic energy is half mv square, and then we know our elastic potential energy is half mv square, and our gravitational potential energy is mgh. Okay, and then typically in oscillation, when you're at now this is going to be the displacement against energy graph. So here we have the amplitude. Okay, 1 second. Here we have the amplitudes, and this is going to be the equilibrium position. And this here is going to be the the maximum displacement. Okay. Now remember that at the equilibrium position, the Ke is max and Pe is going to be equal to 0, potential energy 0. And then at the amplitude, our Ke is going to be equal to 0 and potential energy is going to be equal to max. So I hope you already know what the reasoning behind all of this is as well. Okay, so I'm not going to explain any of that. We're just doing the revision here. And then this is going to be the graph for the kinetic energy, potential energy, and this is the total energy graph right over here. They can ask you to plot any of them really. Now the total energy remains constant because the total energy is equals to Ke plus potential energy, right? And if we look, let's just look at this position right over here, the amplitude. At the amplitude, the Ke is 0 and potential energy is maximum. So total energy is equals to the potential energy max. So potential energy in a spring mass system, let's say, is half K x, which is the displacement. Here the displacement is the amplitude square. Total total energy. Okay. Total energy is equal to half Ka square. All of this is constant, so we have a straight line like that. Okay. So that's all for this. They can ask you to do many things with this. And yeah, but the main thing is just understanding the equations, conservation of energy, and the graph. Okay, so now we're going to be talking about the time period equations. So we can see whenever you have something like this, where you have a thread, and then you have a small ball or a bob. This is like a pendulum, basically, right? So a pendulum is going to have a separate equation, and this is what we call a mass spring system. So you need to be able to identify these systems. First step is always identifying which system are we talking about. And sometimes they will even tell you which we're talking about in exam. So first is identifying. Second is you're going to use the equation of time period. So time period for a pendulum is going to be 2 pi square root L over G. And time period equation for mass spring system is T is equals to 2 pi square root M over K. Okay, where this is the total mass and the total spring constant. So for example, in one past paper, they give you two springs that are connected in, I think it was something like this. If I remember, I think it was 2023 paper. So these are two springs that are connected in series. So when two springs are, and these were identical springs as well, identical spring connected in series. So for this, whenever you're using in the equation, there's going to be the spring constant total. So total spring constant for both of these would be K total is equals to NK, right? Where N is the number of springs. So K total here would be 2K. So, when you solve this equation and you have to get the value of K. So this K here was 2K actually, because it's a total spring constant. Same with the mass as well. This is the total mass, right? So this is a total mass and this is a total spring constant. That's a very important thing that most teachers miss out when they try to explain this, and maybe you're hearing this for the first time as well. So that's an important thing you have to keep in mind. And yeah, I think that's all. And then for frequency, you're just going to flip everything. So for frequency, it's going to be 1 over 2 pi square root G over L. And here frequency is going to be 1 over 2 pi square root K total over M total. Okay. And then some assumptions when we're using these equations. This might pop up in your unit 5 or unit 6. Whenever you're using mass spring equations, remember that we assume the spring obeys Hooke's law, and we assume that the oscillations are small enough so that the spring stays in its elastic limit. It doesn't plastically deform, and then Hooke's law no longer is applied and even obeyed. And then we assume that there's no energy loss and there's no damping, and the mass of the spring is negligible. Okay. And then when we use the pendulum equations, we assume that the angle is small, so that sine x is equals to x. If you want to know a bit more about this, you can go to the playlist video where I derived both of these equations as well. Okay, and then the bob is treated as a point mass. There's no damping and g is constant. Okay, so if they ever ask you why is the time value in real life a little different or the frequency value a little different, you can say that angle is too large, or the bob isn't treated as a point mass, there's damping, g isn't constant, and the opposite for the above as well. Okay, so these are important assumptions. Again, this is often not taught as well, but I hope you are familiar with some of these points. Okay, now I have a little bit of a question here that I kind of just made up. Okay, and then I think I forgot to put the value of k, so let's take k is going to be, let's take a value of 21.7 Newton per meter. Okay, so let's find the frequency of both of these. If the length is 5 centimeter and the mass is 20 grams for the second one, and the first one is just the length that we have to know. So let's find the frequency of the first pendulum, which is going to be 1 over 2 pi square root, in the second square root g 9.81 over 5 times 10 to the raised power of minus 2. Let's find the frequency. So that's going to be 2.23 hertz. So the frequency of this is only dependent on the length. Okay, the length is the thing that determines the frequency. The rest, g is constant and the rest of the stuff is constant. Okay, the second question, we have the spring again and we have a mass. Now for here we're going to do frequency is equals to 1 over 2 pi square root k over m. So I'm going to do 1 over 2 pi square root 21.7 over 20 times 10 to the raised power of minus 3. So this is going to be 5.24 hertz. And you can find the time period as well. Frequency is equals to 1 by t. Okay, so you can use that formula as well. 1 second. Frequency is equals to 1 by t, or frequency is equals to n by t. Okay, so if you have the time period, this represents the number of oscillations. So one oscillation, you have the time period t. If you have n number of oscillations, then you can have any time. Depends. For example, if they say you have 50 oscillations in 1 minute, then n will be 50 and t will be 1 times 60. Okay, so it should be 50 over 60. Okay, that's going to be 5 over 6. So 5 over 6 is going to be 0.833 seconds. And if they say the time period is 20 seconds, then this is going to be 1 over 20. Okay, so 1 over 20, let's do that. We're going to get 0.05 seconds. Okay, so sometimes they ask that as well. Right, so just be familiar with these two equations as well, and this as well. So we're going to jump into the core practical. So for the core practical, we're going to determine the value of an unknown mass using the resonant frequencies of a known mass on the string. So first, let's understand a couple of points. So if an oscillation of a system is free from any influence of any forces from outside the system, then it's called natural or free oscillation. So if there's no force outside the system, it's a natural free oscillation. And the corresponding frequency of the oscillation of a system, if it undergoes free oscillation, is called natural frequency or resonant frequency. Okay, so in a free oscillation, the frequency is the natural frequency basically, right? And we're going to be using the spring mass system. So using the spring mass system, we can say that the time is directly proportional to square root m and t squared is directly proportional to m, right? So what we want to do here is we want to find the value of an unknown mass using the frequency. Okay, so what we're going to be doing now with all of this is we're going to be finding the time period out. And for time period, we need to measure the number of oscillations. Okay, and then we're going to do that. And to help that process out, we're going to place a timing marker. And then we're going to make sure the timing marker is at the center of oscillation. And then it's going to help us to determine the start and end of the oscillation more accurately and reduce uncertainty in time measurement. And then we're going to start the clock and we're going to start the oscillations. And then we're gonna measure multiple oscillations and divide by the number of oscillations. This will help reduce the percentage uncertainty in time. And then you can repeat and calculate mean. This will reduce the effect of random error. So to explain this point a bit more, we know uncertainty, the absolute uncertainty, divide by the time value times 100 is equals to percentage uncertainty. So if we find the time from multiple oscillations, that's going to increase the time value. The absolute uncertainty remains the same, and the percentage uncertainty is going to go down. Okay. Now, after we get a time value, right, we're going to repeat and calculate mean. So we will have a time value. Now, a better way to do this experiment is you can even attach a data logger and a motion sensor. This is to avoid the reaction time. And data logger and motion sensor can take a lot of values and a lot of measurements in a very short amount of time as well. And they can plot graphs for us. So they're really helpful. Okay, and then of course, if you notice, then we went from 100 grams to 300 grams. Okay, and then using all of this, our data logger can graphically show us the results. And then we change these masses and stuff. And so we go from 100 to 200 to 300 for different masses. We find the time period. Okay, is that clear? Different masses, different time periods. We plot a table and then we plot a graph of t square against m. We plot a graph of t square against m, and it's a straight line. And then what we do is we attach an unknown mass and we measure its time period. Okay, and then we measure its time period, so time for 10 oscillations, and then we divide by 10, we get the time period, we square it, and we see where the mass ends up on the graph, and that's going to be the mass of this. Okay, so I was a bit quick with this. Okay, so you can pause. If you are confused anywhere, you can comment, and if it's clear, then we'll move on to the next part. We have a lot of things to get through. So most students find till here the chapter to be quite simple, but when they get to this resonance and damping, it's a lot of theory, and theory is usually where most students struggle with. Okay, so first we'll understand damping. Damping is basically, in Edexcel, the way they like to explain it is, damping is the loss of energy from the mass spring system or the pendulum, or from any system that's in simple harmonic motion. So it's the loss of energy from the system to the surroundings, and that energy doesn't come back. Would that make sense? And in some other boards, they say that it's the loss of energy which causes a decrease in amplitude due to resistive forces. Okay, let me write that down. So there's going to be resistive forces, energy lost from system to surrounding, and it doesn't come back, and amplitude decreases. The energy doesn't come back. Okay, and then three types of damping. Okay, the first is light damping, where the amplitude is going to decrease and decrease and decrease. So it follows this exponential envelope as well. So there's going to be decreasing amplitude of oscillation, but the time period remains constant. Remember that. Okay, so it crosses its mean position a number of times and takes a long time to come to rest. The next thing is that critical damping. Critical damping is the object instantly comes to the mean position or the equilibrium position in the smallest time possible and then stops. Okay, and then we have heavy damping, where the object takes an infinite time and its amplitude decreases really, really slowly, and it takes a lot of time to come to the equilibrium position. And there are no oscillations here as well. Okay, and I want to explain all of this, but it's pretty much the same thing, but just a bit more elaborated and a little bit explained. So you can read through this as well. It's essentially the same thing. So just read through this and hope it's understood. Okay, the next is probably the most important thing in this chapter, because so many questions come up, 6 markers, a lot of stuff, and that is resonance. Okay, resonance in a nutshell is when the natural frequency of the system is equals to the driving frequency of the driving force. Okay, so this is basically when resonance occurs. Okay, so in short, the key points that you have to remember is that resonance, okay, in forced oscillation is where energy is transferred from the oscillator, which causes the driving force to the system. And at resonance, the driving force of xy, okay, which would be the thing causing the driving frequency, is equals to the natural frequency of the zy, which could be the system. Okay, so you have to specify what's the thing that's causing the driving frequency and what's the thing that has the natural frequency. You have to really specify that. I'll show you through an example. And now here another rule, remember, is that driving frequency can also be a multiple integer. So for example, if the natural frequency is 2, right, then your driving frequency can also be 4, right? 2 equals 2 times 2, right? So it's a multiple integer, so that's also possible. So resonance will occur here as well. Okay, and then next point is that there is an efficient or maximum transfer of energy to the system and maximum amplitude occurs. Now usually all of the resonance questions, they will follow the same pattern but with a little twist. Okay, so keywords here is always try to specify whenever you are answering damping or resonance question, always speak in terms of energy transfer from system to surrounding and stuff. So explain in terms of energy. They really like that. Okay, so similar for damping system, examiners keenly look for that energy is transferred from system and is dissipated into heat or something else depending on the context, and energy is lost and doesn't come back. This causes the vibrational energy to decrease and amplitude to decrease. This is such an important thing. Examiners stress that students don't know how to explain this part. So that's why I specified speak in terms of energy. They really love that, examiners. And then typically for 6 markers and stuff, use this format. It works really well. Okay, but obviously don't memorize it. If you memorize it, you're in the wrong place. It's just to help you get the main gist of what the question will be like, the answer structure. But each question has a twist to it. So you will never get the full marks if you memorize this. Maybe you can get some marks. Okay? And then remember, for damped oscillations, the maximum amplitude at resonance decreases in comparison to non-damped oscillations. Okay? And in damped oscillations, energy is transferred from the system. So the transfer of energy to isn't as sufficient. Okay? Now it will sound a little weird what's going on, so it's better to understand it like this. This is the system. Okay? This is our force. And this is the surrounding. Surrounding can be anything else. Your energy is going from the system to it's going from the system, or better say energy is transferred to the system, and then energy is transferred from the system to the surrounding. Okay? So in damping, what happens is the system is getting a lot of energy, but the system is losing a lot of energy, and that causes problems. Okay? And that means the system isn't efficient. Okay? The efficiency goes down. Okay? That's the main point I'm trying to say here. Energy is transferred from the system, which means energy is lost. So transfer of energy to the system isn't as efficient. Okay? So the system gets the energy, but it loses a lot of it, so the efficiency goes down. Okay? So that's an extremely important point. Right? Now next thing is that light, heavy and critical damping shift the frequency at which resonance occurs. The graph moves to the left, but the natural frequency remains the same. Basically, the frequency at which resonance occurs is going to shift, it's going to decrease, but the natural frequency remains the same. So here's the example. So this is resonance frequency without damping. How the graph would look like of amplitude against frequency. And you can see that the graphs are going to infinity. Really, really large amplitude. This is the natural frequency, by the way. Right? And then the usual one that we see in exams are light damping one. Right? Where the driving frequency is equal to the natural frequency, your resonance will occur. That's good. So natural frequency is equal to the driving frequency, right? And then in the other two cases, notice that the graphs at which the point at which the maximum amplitude occurs is shifting away from the natural frequency and it's going to other smaller frequencies. The place where it matches the natural frequency, at which the resonance occurs. So natural frequency is equal to driving frequency. This thing applies for specifically when you have light damping or no damping. And you can see no damping, it's going to infinity, really large amplitude. Okay. So yeah, so this is typically helpful in earthquake systems that we build. Earthquake systems. So these dampings help us out. If you know, I think there's a tower in Taiwan, I think, and one in US as well. That's come up in exam, and those towers have this dampers. Okay. So those are really good as well. To help us out. Okay. I think yeah, that's all. And let's just do one question on this as well. So here we see that a teacher is teaching her class about the phenomena of resonance. To do this, she uses drinking glass to produce two sounds in different ways. She gently struck the glass and it emits sound for a short time. And with a wet finger, she slid around the top of the glass. It is possible to produce a loud, continuous sound. So the answer to this question, I want you to pause and think about it. The first part you have to explain is that gently struck means that is a free oscillation. You just struck it, the system moved for a bit. Okay, free oscillation is better to write. Okay, so the glass was in free oscillation when the glass was gently struck. Second point, the amplitude decreased due to energy transferred to surroundings and energy energy did not come back to system. Okay, or you can say damping. So that's why you have the sound emitting for a short amount of time, because the amplitude of the oscillation decreased. The reason for this decrease is because energy was transferred to the surroundings and the energy did not come back to the system. The third thing you have to mention is the wet finger thing. So wet finger thing is that the wet finger slid around the top of the glass, right? So it was kind of moving around the top of the glass. So there was this continuous force. So basically the wet finger caused the glass to be driven into a forced oscillation by the finger. Forced oscillation. Okay, and driven by a driving frequency. Okay? And the fourth point you have to say is that the loud sound was caused because of the resonance. And the resonance occurred because the natural frequency of the glass was equals to the driving frequency of the finger. Okay? And because of this, there was maximum absorption of energy, and there was the maximum possible amplitude was generated as well. Okay, so that's going to be your answer. Now let me just show you the mark scheme for this as well. So here's the mark scheme of this, and yeah, so you can mention this as well. I have explained this in a lot of detail. I think in an exam walkthrough, I'm not sure if I actually made an exam walkthrough on this question, but I think I did. So you can check through the exam walkthroughs. If I did, I'll link it in the description, so you can check out that explanation. I'll show you a bit more slides. So this is the examiner report for this as well. And then here is a bit more explanation on this question, a bit more detailed explanation. Lastly, we're going to be talking about ductile materials and plastic deformation. And this is the quite easy part of this chapter. It's actually connected to damping itself. So let's just go through this. So ductile materials can be made into wires, so they have high strain. They can change their shape really easily, ductile materials. So they can be made into wires. And now you have to understand these two terms. One is elastic deformation and the other is plastic deformation. Elastic means that you remove the load and the object will return back to its original shape. But with plastic deformation, it's permanently deformed, so it's not going to return to its original shape. And to plastically deform something, you need to give energy. Okay, so to plastically deform a ductile material specifically, to do that, you need to give energy. Okay, so we're not talking about the elastic deformation here. We're talking about plastic deformation, permanent deformation. So if the object is moving in simple harmonic motion, let's say you have a ductile material and let's say you have a rope, okay, rope, and that rope is made of a ductile material, and the rope is moving up and down. Maybe there's a ball here or something like that, and it's moving in simple harmonic motion. So in simple harmonic motion, there is this vibrational energy or the energy of the oscillation. Okay, so this energy is going to be used to deform the material. So from here, energy is going to be transferred to the rope to plastically deform the rope. So your vibrational energy or the energy of the oscillation will go down, it will decrease, and because of that, the amplitude of the oscillation is going to decrease. The spelling of amplitude is incorrect, it should be amplitude. Okay, so this is the same way damping works as well. So this is just damping. Damping is energy lost to the surroundings and it doesn't come back to the system. The same way here as well. Energy is lost from the system and it goes to the rope. Instead of going, so it goes to the rope. Now in the previous examples I gave, I just used to say it goes to the surrounding. But here I'm specifically specifying where the energy is going to. It's going from our system to the rope, to plastically deform the rope, and the rope is made of ductile material, and so the energy doesn't come back, and that's the same as damping. So here this is an application of damping, you can say, and I think that's all. Mostly you get MCQs from this, but there is possibility of 3 markers or 4 markers as well, right? So I just want to make a comment that I was going to attach questions in this as well, but then the video was going to be too long. It would go to 1 hour, 20 minutes, 30 minutes, 40 minutes, and that would be really long video for something that you want to use for your revision. So if you do feel like you need to know more, you want to practice more questions, then I definitely recommend going through the exam walkthroughs. They are really amazing for revision and for practice. This video is more of just covering everything you need to know from this chapter, so you can instantly get the facts and the things that you need in exam, so they click in. But if you want more practice focused material, then you go to the exam walkthroughs. Okay, that's all. Good luck for exams.